What's up guys, this is Massey. Welcome to another video. In this video I want to talk about determinants of matrices and some other topics related to determinants. So first of all, let A be a square matrix of order n by n. Then the determinant of A, which is denoted by A between two lines, or det A, is defined inductively as follows. If A is a 1 by 1 matrix, then we have only one element, and determinant of this matrix is going to be that element. If this matrix is 2 by 2, for example here we have A11, A12, A21, A22, the determinant is going to be A11 times A22 minus A12 times A21. So this times this minus this times this. If A is a 3 by 3 matrix, say 3 by 3, then determinant is going to be A11 times determinant of this matrix minus A12 times determinant of matrix including these elements plus A13 times the determinant of this matrix. Let's see some examples. It says find the determinant of the following matrices. I'm going to say that A is going to be 1, 2, 3, 4. So I'm going to say that's going to be 1 times 4 minus 2 times 3. So 4 minus 6, which is going to be negative 2. So determinant of this matrix is negative 2. Then next matrix is 3 by 3. So determinant of A is going to be 2 times 4, negative 2, 2, 1, minus 1 times negative 3, negative 2, negative 1, and 1, plus 3 times determinant of negative 3, 4, negative 1, and 2. So that's going to be 2 times 4 plus 4, because negative 2 times 2 is going to be negative 4, and minus behind it is going to make it positive. And here we have negative 3 minus 2. Again, negative 2 times negative 1 is positive 2, so minus is going to be negative 2. And here, negative 3 times 2, negative 6, minus 4 times negative 1 is going to be negative 4, so it's going to be positive 4. So that will be 2 times 8 minus 1 times negative 6 and negative 5 plus 3, negative 2. So it's going to be 16 plus 5 minus 6, which is going to be 15. In this example, it says find out the determinant of A and also transpose of A. So the determinant of A is 2, 1, negative 3, 0, negative 2, negative 1, 3, negative 2, and 4. That's going to be 2 times negative 8 minus 2 minus 1 times 0 times 4, 0, minus negative 3, which is going to be positive 3, minus 3 times 0 times negative 2, 0, minus negative 6, which is going to be positive 6. So that's going to be 2 times negative 10, negative 3, and here negative 18. So it's going to be negative 20 minus 3 minus 18 is going to be negative 41. Now let's look at the transpose of A. The determinant of transpose is going to be 2, 1, negative 3, 0, negative 2, negative 1, 3, negative 2, and 4. So that's going to be 2 times negative 8 minus 2, 0 times, so it doesn't matter if we write it, but I'm going to write it, because 0 times any expression is 0, 3 times negative 1 minus 6. So that's why it's negative 6, because negative 2 times negative 3 is positive 6, so minus 6, see here. So that's going to be 2 times negative 10 plus 0, and here it's going to be negative 7 times 3, negative 21. So negative 20, negative 21, so that's going to be negative 41. So we're going to say determinant of A is always equals to determinant of transpose of A. Now in this part, I want to show you how to evaluate the determinant of a 3x3 matrix using series diagram. So we learned that if we have a 3x3 matrix, the determinant can be calculated using this method. A11 times the determinant of this matrix minus A12, the determinant of matrix including these elements, and plus A13, which is going to be the determinant of this matrix. Then when you distribute it and simplify it, you're going to get this. Instead of that, there is another method. It's called series method. So here I'm going to list all the elements: A11, A21, A31, A12, A22, A32, A13, A23, A33. Then I'm gonna write the first two columns again: A11, A21, A31, A12, A22, and A32. Then I'm gonna have so that means it's going to be A11 times A22 times A33 plus A12 times A23 times A31 plus A13 times A21 plus A32 minus A31, A22, A13 minus A32, A23, and A11 minus A33, A21, and A12. So I'm going to list it here. So determinant of A is going to be A11, A22, A33 plus A12, A23, A31 plus A13, A21, A32 minus A31, A22, A13 minus A32, A23, A11 minus A33, A21, A12. That's the determinant of this matrix using series diagram. Now let's solve this example using series diagram. So I'm gonna have 4, 1, negative 2, 2, negative 3, 5, 3, 0, 2, and I list the first two columns again. So it's going to be minus so I'm going to say 4 times negative 3 times 2 plus 2 times 0 times negative 2 plus 3 times 1 times 5 minus negative 2, negative 3, 3 minus 5 times 0 times 4 minus 2 times 1 times 2. So we get here negative 12, negative 24. This one is 0. This one is 15. Here we have positive 6, 18, negative 18. This one is going to be 0. And here this one is going to be 4. So we have negative 3, negative 7 with this guy, and we have negative 31 is the determinant of this matrix. So that's how we use series method in order to find out the determinant of 3x3 matrix. So now let's look at the concept called minors. Here in this example it says find the minors M11, M12, and M23 of the following matrix. M11 is gonna be when you basically delete the row and column on this element, which is 1, 1, 1. The rest is gonna be a matrix 2 by 2, as you see in here. So it's gonna be the determinant of 1, 3, 0, negative 4. M12, as you see here, it's this element, that's A12. And if we remove the row and column on the same element, and it's gonna leave us these 4 elements. So we have 5, 2, 3, -4. And finally, M23 is gonna give us, that's 2, and here is gonna be 3. So when we remove this row and column, so it's gonna be 4, 3, 2, 0. These are the concept of minors. Now let's look at the determinant. 1 times -4 is -4, minus 0 is still -4. 5 times -4 minus 2 times 3, which is going to be -20, minus 6, that's -26. Next one, 4 times 0, 0, minus 2 times 3, which is -6. So these are the minors of these elements. Now the next topic is cofactor. Let a matrix consist of aij be an n by n matrix for any I equal or greater than 1 and j equal or less than n. The factor of aij, the cofactor of aij, is defined as -1 to the power of I plus j times the minor ij, where mij is the minor of aij, that is the determinant of n minus 1 times n minus 1 matrix obtained from A by deleting the ith row and the jth column in A, exactly like what we saw in previous example, multiplied by -1 to the power of I plus j, and the cofactor of aij is denoted by aij, A capital, is given by this formula. So cofactor of lowercase aij equals to capital Aij, which is -1 to the power of A plus j times mij. Let's see the example now. Find the cofactors of the following matrices. So it means that we need to find A11, A21, A12, and A22. A11 is going to be -1 to the power of 1 plus 1 times the determinant of 4. Next one, -1 to the power of 2 plus 1, 2, 1. When you remove it, we have just 2. Next one, -1 to the power of 1 plus 2 is going to be 1. And then we have -1 to the power of 2 by 2, which is going to be 3. So that's going to be positive 4, -2, -1, and this one is going to be positive 3. So that's A11, A21, A12, and A22. These are the cofactors of this matrix. Now let's look at the cofactors of the 3 by 3 matrix. So I'm going to say A11 will be -1 to the power of 1 plus 1, removing this row and column, 2, 6, 0, -3. A12, -1 to the power of 1 plus 2 is going to be 4, 6, -1, -3. A13 is going to be -1 to the power of 1 plus 3, 4, 2, -1, 0. A21, -1 to the power of 2 plus 1, that's 2, and this is 1, so it's going to be 3, 1, 0, 3. 3, 1, 0, -3. A22, -1 to the power of 2 plus 2, that's going to be 2, 1, -1, -3. And next one is going to be A23, -1, 2 plus 3, 2 and 3 is going to be like that, and 2, 3, negative 1 and 0. So that's going to be the sixth of them. And now we have a 3, 1, negative 1 to the power of 3 plus 1. So that's the third row and this column. So it's going to be 3, 1, 2, 6. Then we have a 3, 2, negative 1 to the power of 3 plus 2. 3 and 2, 2, 4, 1, 6. And here we have a 3, 3, negative 3, 1 to the power of 3 plus 3. That's going to be 2, 3, 4, 2. Now, for any square matrix A of order n by n, and for any scalar s, the determinant of s times A equals to s to the power of n times determinant of A. For example, if A is a matrix 3 by 3 and in which each row is in geometric progression, that is A, AR, AR squared, B, BS, BS squared, and C, CT, and CT squared. What we need to do, we need to show that the determinant of A equals to A times B times C times R minus S times S minus T times T minus R. So what we need to do, I'm gonna say determinant of A is, we take A out, 1 R R squared, B BS BS squared, C CT CT squared. So basically you factor A from the first row. Now if you factor the B from the second row, it's going to be AB 1 R R squared, 1 S S squared, C CT CT squared. And then you can take C out, A B C, 1 R R squared, 1 S S squared, 1 T T squared. And after that, we can basically start finding the determinant of this part. But before that, let's make these two elements 0. So I'm going to change R2 to R2 minus R1. So it's going to be A, B, C. R1 remains the same. R3 remains the same. However, R2 is going to be 1 minus 1, that's 0, S minus R, and this one is going to be S squared minus R squared. And then, what we need to do, we need to do the same thing with R3, the third row, R3 minus R1. So it's going to be 1 R, R squared, 0, S minus R, S squared minus R squared, and here we're gonna have 0 T minus R, T squared minus R squared. Then you can factor S minus R from this row. Basically you multiply it by S minus R. So we have 1 R R squared, 0 1 S plus R, because S squared minus R squared is going to be divided by S minus R is going to be S plus R. And we write the third row the same. Then I can factor T minus R as well. So it's going to be A, B, C, S minus R, T minus R, 1 R R squared, 0 1 S plus R, 0 1 T plus R. And then we find a determinant here. That's gonna be A times B times C, S minus R, S minus T, and T minus R, because the determinant of this part is gonna be S minus T. So that's gonna be the final answer. Now next topic is adjoint of A. It says let matrix A is Aij, contains of this elements be a square matrix, then adjoint of A is defined as the transpose of a matrix Aij, where Aij is the ijth factor in A. The adjoint of A is denoted by adjoint A or adj A. The ijth entry of adj A is the jith cofactor in A. Let's find out an example. That's going to be easier if you do it through an example. So now I want to find out the cofactor for A11, A12, A13, A21, A22, A23, A31, A32, and A33. So A11 is going to be, you remove the row and column in here, so it's going to be -1 to the power of 1 plus 1, which is 2. Determinant of 1, -2, 2 and -4. 1 times -4 is -4, plus 4 is going to be 0. Then you have -1 to the power of 1 plus 2, which is 3. That's this one. 3, -1, -2, -4. 3, -1, -2, -4. It's going to be 14. Next one, 1A3. A13, so it's going to be this one. So -1 to the power of 4. 3, 1, -1, and 2. So 3 times 2 is 6, plus 1, 7, times 1, 7. Next one, A21. 21 is going to be this. It means that we need to remove this row and column. 3, 2, 2, and 4. -4. That's -4. So that's going to be -3 times -4, -12, minus 4 is going to be -16, times -1 is going to be +16. A22 is going to be -1 to the power of 4. A22 is this one. You remove this row and column. You have 4, 2, -1, and -4. 4, 2, -1, and -4. 4 times -4, -16, plus 2 is going to be -14, times 1 is negative, still remains as -14. A23 is going to be this one. Remove this row and column. 4, 3, -1, and 2. That's going to be 8 plus 3, 11, times -11. A31 is this one. 3, 1, 2, -2. 3, 2, 1, -2. And that's going to be -6 minus 2, -8, times +1 is going to be -8. A32 is going to be -1 to the power of 5. 3, 2 is going to be this one. We remove this row and column. 4, 3, 2, -2. 4, 3, 2, -2. So that's going to be -8 minus 6 is -14, times -1 is going to be +14. Then you have A33, -1 to the power of 6. We remove this row and column. 4, 3, 3, 1. That's going to be 4 minus 9, which is going to be -5, times 1 is going to be the same, 5. Therefore, we can say adjoint of A is going to be a matrix. Transpose of a matrix consists of all these cofactors, which is going to be 0, 14, 7, 16, -14, -11, and you have -8, +14, and -5. So that will be 0, 14, 7, 16, -14, -11, -8, 14, -5. So that's going to be the adjoint of A. So I need to mention that square matrix A is invertible if and only if the determinant A is non-zero, and in this case is gonna be inverse of A equals to 1 over determinant of A times adjoint of A. This is extremely important. Inverse of A equals to 1 over determinant of A times adjoint of A. Or we can say determinant of adjoint of A equals to A to the power of n minus 1. Let's see an example. It says find real numbers of A and B, lowercase a and b, such that A plus B times capital A, or matrix A, plus A squared equals to 0 when A is the matrix 2 by 2. So A is 3, 2, 1, 1. A squared is going to be 3, 2, 1, 1. 3, 2, 1, 1. It's going to be 9 plus 2, 11. 6 plus 2, 8. 3 plus 1, 4. 2 plus 1, 3. That's A squared. So we can say, since they need to have the same dimension, we can say A, which is a number, so it's going to be identity matrix, plus B times A, which is you multiply B by all the elements in here, 3B, 2B, 1B, 1B, plus A squared, which is 11, 8, 4, and 3, equals to 0. Then you're going to say, when you add them, A plus 3B plus 11, here you have 2B plus 8, here you have B plus 4, and here you have A plus B plus 3. And that's supposed to be equal to 0. So A plus 3B plus 11 is 0. 2B plus 8 is 0. B plus 4 is 0. A plus B plus 3 is 0. So we can say, based on that, B is negative 4. When you sub it there, A will be positive 1. So when we sub it in the formula, when we have A plus B, A plus A squared, we can say 1 minus 4A plus A squared equals to 0. If we multiply all these terms by inverse of A, which is going to be inverse of A minus 4A times inverse of A plus A squared times inverse of A, that will lead us to inverse of A minus 4 plus A, which is going to be inverse of A is going to be equal to 4 minus A. So 4 is 4, 0, 0, 4, and matrix of A is defined here 3, 2, 1, 1. That's going to be 1, negative 2, negative 1, and 3. That's the answer. Now in this example it says find adjoint of A, determinant of A, and inverse of A, where A is 3, 2, 1, 1. Let's start with determinant of A. That's going to be 3 times 1 minus 2 times 1, which is going to be 1. And then we can find out the adjoint of A. We need to find A11, A12, A21, and A22. So it's going to be negative 1 to the power of 2. When we remove this, we're going to have only 1. Negative 1 to the power of 3. When we remove this, it's going to be 1. Negative 1 to the power of 3. To 1 is going to be 2. And then negative 1 to the power of 4. Remove this and you end up with 3. So that's going to be 3. This one is going to be negative 2, negative 1, and positive 1. So adjoint of A is basically transpose of this matrix, which we already got these numbers, 1, -1, -2, and 3 transpose. That will be 1, -1, -2, and 3. So that's the adjoint. If we want to find out the inverse of A, that's going to be 1 over determinant of A times adjoint of A, which is going to be 1 over 1, because the determinant is 1, 1, -2, -1, and 3, which is going to remain the same thing. That's going to be the final answer. If A is a square matrix and I is the corresponding unit matrix, then the polynomial determinant of A minus x times I in if x is called characteristic polynomial of A, and the equation A minus xi equals to 0 is called characteristic equation. So we have characteristic polynomial and we have characteristic equation of the matrix A. Let's see this example. It says find the characteristic polynomial and characteristic equation of this matrix 2, 1, 1, -1. So A is 2, 1, 1, -1. Determinant of A minus xi will be 2 minus x, 1, 1, -1 minus x, because you subtract it from x times I. So determinant is going to be 2 minus x times -1, -x, minus 1. Which will be, you take the negative out and multiply it here, is going to be x minus 2, x plus 1, minus 1. Which is going to be x squared minus x minus 3 equals to 0. So I'm going to say x squared minus x minus 3 is the characteristic polynomial, and x squared minus x minus 3 equals to 0 is characteristic equation. Now in this example, it says find the characteristic polynomial and the characteristic equation for A given by this 3 by 3 matrix. So we follow the same rule. So A minus xi, which is going to be, basically that's the determinant of this, which is going to be 1 minus x, -1, 2, 0, 2 minus x, 1, -1, 0, 3 minus x. Now we need to find out the determinant. It's going to be -1 minus x times 2 minus x times 3 minus x minus 0. Negative times -1 is going to be positive. 0 times this guy is going to be 0 plus 1, because negative times negative is going to be positive, plus 2 times 0 times 0 minus -1 times 2 minus x, which is going to be 2 minus x. So that's going to be 1 minus x times 2 minus x times 3 minus x plus 1 plus 4 minus 2x. So now we distribute it. It's going to be 1 times 1, 1 times 2, 2, -x, -2x plus x squared times 3 minus x plus 5 minus 2x. Then we have 6 minus 2x minus 3x plus x squared minus 6x plus 2x squared plus 3x squared minus x cubed plus x minus 2x. Then we have x cubed. Then we have this 3 is going to be 6x squared. Then we have -2x and -3x is going to be -5x. With this negative 6x, it's going to be negative 11x. With this negative 2x, it's going to be negative 13x. And then, here we had negative in here. And then we have only this here, we have plus 5, and we have plus 6. So it's going to be equals to, that's the basically characteristic polynomial. If we make it equal to 0, we're going to get the characteristic equation. So we multiply it by negative 1 to get rid of this. That's the now characteristic equation. Now in this example, we have the characteristic equation that we found in previous examples, I think 2 examples ago. And now we need to show that the matrix A satisfies its characteristic equation, and then we need to find out the inverse of A. So we have x squared minus x minus 3. So we need to have A squared, which is 2, 1, 1, negative 1 times 2, 1, 1, negative 1. 2 times 2, 4 plus 1, 5. 2 times 1 minus 1 is going to be 1. 1 times 2 minus 1, 1. 1 times 1 plus 1 is going to be 2. So therefore, we're going to say A squared minus A minus 3 equals to 0. 5, 1, 1, 2 minus 2, 1, 1, negative 1 minus 3, 0, 0, 3. It's going to be 5 minus 2, 3, minus 3 is going to be 0. 1 minus 1 minus 0 is going to be 0. 1 minus 1 minus 0 is going to be 0. 2 minus 1, 2 minus negative 1 is going to be 3. Minus 3 is going to be 0. Perfect. So it means that that satisfies its characteristic equation. So we showed that this matrix satisfies its characteristic equation. Now if we want to find out the inverse, we're going to say A squared minus A minus 3. We multiply them by inverse. That's going to be A minus I minus 3. So it's going to be negative 3 inverse. It's going to be equal to negative AI, which means that inverse is 1 over 3 A minus I. So which will be 1 over 3, 2 minus 1, 1, 1 minus 0, 1, negative 1 minus 0 is 1, negative 1 minus 1 is going to be negative 2. So it's going to be 1 over 3, 1 over 3, 1 over 3, negative 2 over 3. That's the inverse of this matrix. Now I want to show you what is idempotent matrix. Idempotent matrix, when a square matrix is basically satisfying A squared equals to A, we call this matrix a idempotent matrix. So that the matrix A is idempotent matrix. As you see here, we have 3 by 3 matrix. We need to find out A squared, which is going to be 2, negative 2, negative 4, negative 1, 3, 4, 1, negative 2, negative 3, times 2, negative 2, negative 4, negative 1, 3, 4, 1, negative 2, negative 3. So when you multiply, you have 2 times 2 plus negative 2 times negative 1 plus negative 4 times 1. That's going to be 4 plus 2 minus 4. That's 2. Then 2 times negative 2 plus negative 2 times 3 plus negative 4 times negative 2. So it's going to be negative 4 minus 6 plus 8. That's going to be negative 2. 2 times negative 4 plus negative 2 times 4 plus negative 4 times negative 3. So it's going to be negative 8 plus 12. That's going to be negative 4. Negative 1 times 2. 3 times negative 1, 4 times 1. It's going to be negative 2, negative 3, and positive 4, which will be negative 1. Negative 1 times negative 2 plus 3 times 3 plus 4 times negative 2. It's going to be 2 plus 9 minus 8. That will be 3. Then you have negative 1 times negative 4. That's 4. 3 times 4, 12. 4 times negative 3 is going to be negative 12. So it's going to be 4. And after that, 1 times 2 plus negative 2 times negative 1 plus negative 3 times 1, which will be 1. Then you multiply this. 1 times negative 2, negative 2 times 3, negative 3 times negative 2, that will be negative 2, negative 6 and plus 6, that will be negative 2. And finally 1 times negative 4 plus negative 2 times 4 plus negative 3 times negative 3, that will make me negative 3, basically negative 4, negative 8 and positive 9. That will be the a squared. So as you see here, they are equal. So a squared equals to a, so we call it a idempotent matrix. Next topic is nilpotent matrix. A square matrix A is called nilpotent matrix if there exists a positive integer m such that a to the power of m is a zero matrix. Zero matrix is those that have 0 for all the elements. Among such positive integers m, the least positive one is called the index of the nilpotent matrix. So we have two concepts. One, nilpotent matrix, and the second one is index of the nilpotent matrix. So let's see if A equals to 0, 1, 0, 0 is a nilpotent matrix and matrix of index 2. So we have 0, 1, 0, 0 times 0, 1, 0, 0. 0 times 0 plus 1 is going to be 0. 0 times 0 is 0. 0 times 0, 0 times 0. 0 times 1, 0, 0 is going to be 0. So since it's equal to 0, we call it a nilpotent matrix. We can say every 0 square matrix is a nilpotent matrix of index 1. Next concept is involuntary matrix. A square matrix A is called involuntary if A squared is equal to unit matrix of the same order. So if it's equal to 0, we're going to call it a nilpotent. If it's equal to a unit matrix, we call it a involuntary matrix. So note that a square matrix is involuntary if and only if inverse of A equals to A. So now verify if 0, 1, 1 and 0 is an involuntary matrix. So I'm gonna say 0, 1, 1, 0 times 0, 1, 1, 0. Supposed to be 2 by 2. 0 times 0 plus 1 times 1, 1. 0 times 1 plus 1 times 0, 0. 1 times 1 plus 0 times 1, 0. 1 times 1 plus 0, 1. So it is an unit matrix. So you can say A is an involuntary matrix. And finally, the last topic is periodic matrix. A square matrix A is said to be a periodic matrix if A to the power of k plus 1 equals to A for some positive integer of k. If k is the least positive integer such that A to the power of k plus 1 equals to A, then k is called a period of A. Show that A is periodic matrix and find its period. A equals to I, 0, 0, negative I. So A squared, if we figure out, is going to be I, 0, 0, negative I times I, 0, 0, negative I. that will be I squared 0, 0, positive I squared. Yep. So that will make it as negative 1, 0, 0, negative 1. Now if we multiply a squared by a squared, you're gonna get negative 1, 0, 0, negative 1 multiplied by negative 1, 0, 0, negative 1. That's gonna give you 1, 0, 0, 1, which is I. Now if you multiply it by the first matrix, which is A, let's say A5 is 8 to the power 4 times A. That's gonna be equal to A. So A to the power 5 equals to A. So we're gonna say A is a periodic matrix and period is 4, because 4 plus 1 is 5. So that's the end of this part. I hope you enjoyed this video. Please don't forget to subscribe this channel and please recommend it for your friends. Thank you for watching and have a great day.